All right, our next topic is space. We're going to start with the macro and make our way to the micro. Macro meaning the big picture, and then look at the small. Um, Obviously, what we know about the universe is that we are a part of a galaxy that's in a universe of billions of galaxies. And so in our galaxy, we're going to talk about, which is the Milky Way, we're going to talk about some of the stars that are found in our galaxy. More specifically, the life cycle of these stars. All right, so if you are not aware, what are stars? Stars are large balls of hot gas. That's right, they're not the star twinkly shape that you're used to. They're actually just a big ball of gas. They look very small because they are very far away, but in fact, there are many bigger and brighter stars than our own sun. One of the slides that we don't have time for is we talk about apparent magnitude and absolute magnitude. And apparent magnitude is based off of what it looks like from Earth. And so obviously the sun, our sun, is closer to us, so it's going to appear to be the biggest star out there. But in reality, it's absolute magnitude. The sun is not the biggest star out there. There are quite a few bigger and even brighter stars. The heat of a star is made in the center by nuclear fusion reaction, and because of the different types of chemicals that make up a star, we have different colors and sizes of our stars. So we have learned that stars are classified by their size, mass, brightness, color, temperature, spectrum, and age. Some types of stars include main sequence stars, red giants, and supergiants, white dwarf stars. A star can be classified as one type of star early in its life cycle and then be classified as another star when it gets older. The life cycle for an average star, such as our sun, includes different stages. The first stage is star formation. The second and longest stage is the main sequence. The third stage of a star can become a red giant or a super red giant, and the last stage is a white dwarf. The beginning and the end of stars. The beginning, a star enters the first stage of its life cycle as a ball of gas and dust. And what happens is gravity pulls that gas and dust together, and hydrogen starts changing into helium through the process of nuclear fusion. When a star is about towards the end of its life cycle, it means it's slowly losing its materials, but sometimes it can lose its materials in a big explosion, which you're all familiar with as your supernovas. Much of a star's material returns to space, or it sometimes forms a new star. Because as we learned with the law of conservation, energy is neither created nor destroyed, it's simply transformed. And so again, we live in a Milky Way galaxy, which is a spiral galaxy if you're not aware of it. And in our galaxy alone, you can clearly see on a clear night 4 billion stars that you can see with just your bare eye. And imagine the amount of stars you can see if you actually use a telescope. Let's talk about starbirth. New stars and planets are born in vast clouds of interstellar gas and dust in a process that can take millions of years. The gas clouds that give birth to a stars are known as molecular clouds, and they're made of hydrogen gas. While most of the hydrogen is spread out incredibly thinly across space, denser clumps can form if something disturbs the cloud. Once that happens, the clumps of gas may begin to shrink due to gravity and pull in more gas, concentrating it in their centers. Eventually, the core regions become so dense and hot that the stars ignite. These brilliant newborn stars may illuminate the clouds in which they form, creating a dazzling display of light and color. So here's your life cycles of a star. Star births. All stars are born from clumps of gas and dust that contract under the influence. Contract means come together. Of gravity to form hot spinning structures called protostars, which is here. Starbirth clouds are found and scattered throughout the spiral arms of the Milky Way as well as in the other galaxies. So you get your protostars being formed from those gases and dust. What we didn't have a discussion about is that in our Milky Way, which is a spiral galaxy, we have a lot more gas and dust, which means we, in our Milky Way galaxy and all galaxies that are spiral, because there's more gases and dust, they have more starbirths being created. So more stars can be made from the gas and dust surrounding us. Let's talk star babies. The youngest star in our Orion Nebula are still surrounded by dense disks of gas and dust. The Hubble Space Telescope has photographed 30 of these disks, which are known as propellets. Planets may eventually form from the gas and dust inside of them. So that would be their star in the middle, and planets will form around it from the star and dust around it. All right, so let's talk about how a star is formed in using this illustration. So it all starts with clumps forming. You have pockets of gas forming a molecular cloud, which is just a huge cloud of cold, dark gas and dust. From them, the clumps start to contract, which means coming together, and they shrink and pull more gas around it with the use of gravity. And then you start getting a spinning disk. The clump shrinks to form a hot, dense core surrounded by a spinning disk of matter. Jets of gas shoot out from its poles. The star ignites, which means you have the birth. When the center is hot enough, nuclear fusion begins and a star is born. A disk of matter still orbits the young star. Disk disperses. The leftover material is either dispersed into space or clumps together to form planets, moons, and other objects. And so this formation of stars is the exact way that our solar system has formed after our sun was created. So once a star is born, it gets into its next step, which is called the main sequence. And a star will spend 90% of its life here in the main sequence. The mass of a star determines its location on the main sequence. So stars can shine as long as they can maintain the delicate balance between the inward pull of their own gravity and the outward pressure of the energy from the core. How long this lasts depends on how much matter a star starts off with. Massive stars have relatively short lives because they quickly use up their hydrogen fuel in nuclear reactions. The most massive stars die in stupendous explosions called supernovas. Small stars have less fuel, but they use it slowly and can last for hundreds of billions of years before they gradually fade away. Medium mass stars, like our sun, evolve along in an intermediate path and end up as a beautiful object called planetary nebula when they die. So here's the depth or the life cycle of a low and medium mass star. So small stars to average size stars like our sun. It goes from main sequence, again, where it spends 90% of its time, and then its next stage will be red giant, planetary nebula, and a white dwarf. So we've already talked about how stars are classified by size, mass, brightness, color, temperature, spectrum, and age. So let's talk specifically about main sequence. When I say main sequence, that means it's entering its second and longest stage of its life cycle. So for example, for you, you are a baby. Your main sequence, if we're put into human terms, would be your time from when you were pretty much a toddler until you were almost elderly. That's your main sequence, where you're spending 90% of your time. And again, what kind of star is our sun? So I asked you what type of star was our star, the sun. And again, it's just an average star. Our sun is an ordinary star that looks huge to us because it's so close. Sun-sized stars have two layers through which energy moves outward from the core, which is an inner layer where it travels by radiation, and an outer layer that carries it by convection, which is rising and falling currents. In larger stars, these two layers are the other way around, while some smaller stars have only a convection layer. Like all stars, the sun has a brilliant surface that emits light and heat. The reason stars are considered main sequence stars and the reason they spend 90% of their time here is because at this stage, that means they are still fusing hydrogen atoms to form helium atoms in their cores. Most of the stars in the universe, which is about 90% of them, are main sequence stars. The sun is a main sequence star. These stars can range from about the 10th of the mass of the sun up to 200 times as massive. So if you look along here, this is the main sequence. And so stars that are here are again still generating helium in their atoms. And as you can see, this is where our sun lands on that spectrum. It's average, it's not the biggest star, it's not the smallest, it's average. Just a picture of Alpha Centauri. So how do stars shine? The energy produced by a star is released by nuclear fusion in its core. This process involves the nuclei, which is the central parts of atoms joining together to make more massive nuclei. Fusion can only occur at an extremely high temperature present in star cores. So your hydrogen goes in, fusion means they come together, creates helium, which generates energy. And that's why we start seeing your sun shining. And this is what happens in our sun and other sun-sized stars. But like all things, there is an end. And so stars begin to die when they run out of hydrogen and gravity begins to take over. Stars begin to shrink, outer core of hydrogen begins to fuse. The outer parts of the star get bigger. So if we get a red giant, that means the star is dying and it's in its last stage of its stellar evolution. So for example, this is a famous star called Betelgeuse, and it's a red giant star. So that means it's a dying star. So what does that mean for our sun? Well, in only a few billion years, our own sun will turn into a red giant star, expand and engulf the inner planets, possibly even Earth. So this is how big they expect our sun to get when it becomes a red giant. And so again, keyword is in a few billion with the B years, so for a long time from now, not in your lifetime, they do expect this sun to eventually die and to expand and become a red giant. Stars spend approximately a few thousand to 1 billion years as a red giant. So even when they start to die, it's not a quick process. It still takes a very long time for a star to die. Eventually, the helium in the core runs out and fusion completely stops. The star will start to shrink again until a new helium shell reaches the core. When the helium ignites, the outer layers of the star are blown off in huge clouds of gas and dust known as planetary nebula. The core will continue to collapse in on itself. Smaller stars, such as the sun, end their lives as compact white dwarfs. In the final stages of its life cycle, a star that has the same mass as the sun, which is again a main sequence star, or smaller, can be classified as a white dwarf. A white dwarf is a small, hot dim star that is the leftover center of an old star. It has no hydrogen left and it will not generate any more new energy, but it can shine for billions of years before cooling completely. So again, even once it's completely down to its last final stage, it still takes a long time for it to finally be completely out. And so our sun, once it hits its red giant stage, again, it will have billions of years after that, then it will eventually become a white dwarf. In what constellation is there a white dwarf in our galaxy? White dwarfs, again, are main sequence stars which have burned through their reservoir of both hydrogen and helium, passed through the giant phase. They were hot enough to ignite their carbon, puffed out their outer layers to form colorful planetary nebulas, and then collapsed and cooled into small glowing coals. This beautiful Hubble telescope image shows a nearby white dwarf in the outer layers of the former star's atmosphere, which have been blown away. The resultant planetary nebula will shine for the next 20,000 to 50,000 years, expanding outwards and fading slowly with time. So here's your white dwarf, which is your leftover core of an old star. So it started from a star that was either the size of our sun or smaller, became a red giant, and now it's ended its life here. And so all the outer shell and the gases and stuff are surrounding it, what was left over from the star. And that's all it is that core. And again, it will shine for a couple thousand years, and then eventually it will go out. Another picture of a white dwarf surrounded by its nebula. Did you figure out which constellation in our galaxy had the white dwarf? Well, it's Sirius. Sirius. When stars get old, when main sequence stars get old, such as our sun, they become red giants and then white dwarfs at the end of their life cycle. But as we know, our sun is an average star. So what happens to those super big stars? And so massive stars, they generate much more energy and they also don't last as long. Massive stars may explode with such intensity that they may become supernovas, neutron stars, pulsars, or black holes. A massive star is a star with a mass 8 times greater than that of the sun. So 8 times or bigger than our sun. It is difficult for stars to get this large as the number of factors influence stellar development, and these factors often limit size. But astronomers have been able to observe massive stars up to 150 times larger than the sun, illustrating that it's possible under right conditions. The life cycle of a massive star is slightly different than the life cycle of an average star. And so they still have their main sequence where they're still generating generating hydrogen into helium, doing nuclear fusion. But after that, they enter what's called the red supergiant stage. They create supernovas, and then they end as a neutron star, a pulsar, or a black hole. Most stars exist in a stable state through a delicate balance between two forces: gravity, which pushes matter inward, and pressure generated by energy released from the core, which pushes matter outward. So, forces are in balance. In a normal star, the inward push of gravity balances the outward pressure. That's okay. It's balanced. That's what's supposed to happen. But when a star starts to die, the core of old stars heat up. They start getting hotter and hotter. The extra heat boosts in outward pressure, so the star swells. So because of extra heat, the star starts to expand. That's why it's called a red giant. All that extra heat is just like one last boost of all the little thermal energy it has left. However, when a particularly large star dies, gravity may cause its core to collapse to form a black hole. Let's talk about your supernovas. A supernova is a gigantic explosion in which a massive star collapses and throws its outer layers into space. Here is a picture called supernova NGC 6826, and its green gas is almost half of its mass. Supernovas can briefly outshine entire galaxies and radiate more energy than our sun will in its entire lifetime. They're also the primary source of heavy elements in the universe. According to NASA, supernovas are the largest explosions that take place in space. After a supernova, you get what's either a neutron star, a pulsar, or a black hole. So let's talk about the neutron star. After the supernova explosion, the center of the collapsed star contracts to form a new star. Remember, the center has to come back together. With average stars, that's why we get white dwarfs. But with a supernova and massive stars, you're going to get a neutron star. And because it's such a violent explosion with the supernova, it has been when the star contracts, it has been smashed together so forcefully that all of the particles have become neutrons. Neutron stars are easy to recognize for astronomers because they bend the light around them. It makes it easy to find them with infrared telescopes, and they are very rare. They are the tiniest, densest stars known. A pinhead size of matter has more mass than the largest supertank on Earth. So that's for it to be so small because they're so packed together, and all those neutrons, they're very heavy, very dense. It can pack the whole mass of the sun into an area the size of Boston. Some rotate as fast as 700 times per second, and it's estimated there are 100 million in our Milky Way galaxy. Neutron stars' solid surface is 1,000,000 times stronger than steel. A supernova explosion can also create a pulsar, and a pulsar is a neutron star that emits flashes or beams of radiation that sweep through Earth's line of sight. Like a black hole, it is an endpoint to stellar evolution. The pulses of high-energy radiation we see from a pulsar are due to a misalignment of the neutron star rotation axis and its magnetic axis. So because the star is kind of on its side or whatever, it emits a light but it's not that it's generating any new energy. It's just emitting what it has left over. Astronomers have discovered around 2,000 pulsars since 1967, and they have powerful magnetic fields that send out radio waves. Slow ones send out 5 pulses per second, and fast ones can send out 716 per second. Everyone's favorite is black holes. Sometimes the leftovers of a supernova are so massive that they collapse to form a black hole. A black hole is an object that is so massive that even light cannot escape its gravity. Black holes are invisible. Their extreme gravity can cause light to stretch. Their spinning can drag the very fabric of space around it. Random facts about black holes. There could be tens of millions of black holes in the Milky Way galaxy. Some scientists think black holes may be evaporating and disappearing over time by leaking heat energy. The swirling clouds of matter around a supermassive black hole are the brightest object in the universe. And some black holes rotate thousands of times per second. This year, they had their very first real image of a black hole, which looks like this. Up until this point, most pictures that we've seen are computer generated, simulated. And so this is an actual picture of a black hole. Last but not least is a quasar. And a quasar is believed to be a supermassive black hole surrounded by an accretion disk. An accretion disk is a flat disk-like structure of gas that rapidly spirals around a larger object, like a black hole, a new star, a white dwarf, etc. A quasar gradually attracts this gas and sometimes other stars or even small galaxies with their super strong gravity. These objects get sucked into a black hole. When a galaxy, star, or gas is absorbed into a quasar in such a way, the result is a massive collision of matter that causes a gigantic explosive output of radiation, energy, and light. This great burst of energy results in a flare, which is a distinct characteristic of a quasar. And so, the light, radiation, and radio waves from these galaxies and stars being absorbed into the black hole travel billions of light years through space. So when we look at quasars, which are 10 to 15 billion light years away, we're actually looking 10 to 15 billion light years into the past. Pretty amazing, right?